Hey everybody, welcome back. So today we're going to talk about star classes. Now we've talked about how I can get the luminosity if I know the flux, how much bright it seems to my eye, and how far away it is, which I get from the parallax. From that I can calculate how bright the star really is, its luminosity. We also talked about how we can get the temperature. You get the temperature if you know the peak wavelength, and then you use Wien's law. You plug that peak wavelength in the formula and then you get the temperature. If I know the luminosity and the temperature, then I can plot them on those graphs that we've been talking about where I've got luminosity this way and temperature this way. And instead of plotting the entire curve, I'll just plot that one dot that represents the peak. Now I can do that for hundreds of stars. When I do that for a bunch of stars, I start to see that there are patterns that form. Almost all of the stars, 90% of the stars, fall into this one type of star we call the main sequence. Then we see giants, we see supergiants, all these different types of things. But we classify the stars using a tool called the Hertzsprung-Russell diagram, but that's too many words to say. So we'll almost always call it the HR diagram. So that's what we're going to look at today is what classes of stars are there out there. Let's get started. All right, so when we look at all the stars in the galaxy, and what this is a Hubble Space Telescope picture pointing towards the center of our galaxy, so we get lots and lots of stars. Everything that you see here in this picture is a star. And remember that the size of the dot actually tells you the brightness of it. It's not telling you the size of the star, but the amount of energy that it's getting basically overexposes the CCD picture that we've talked about before. So we've got some very bright stars and we've got some very dim stars here. The most luminous stars in the galaxy that we have ever found have been about 1 million solar lumens, 10 to the 6 solar lumens. So that's 1 million times brighter than the sun. The sun is incredibly bright. If you stare at it, you're going to go blind. Now imagine that we've got one that's 1 million times brighter. The dimmest stars then are 10 to the minus 4, so 0.0001 times the brightness of the sun. These things are so dim that even though they might be close to us, you're going to have a hard time seeing them just because they're not putting out a whole lot of energy. So there's a huge range from the least luminous to the most luminous, and we'll talk about what we're going to have to do to deal with that here in just a little bit. When we're looking at the temperature, remember we get the temperature from Wien's law. We look at that peak wavelength. So I can just sit here and look at the peak color for each of these stars and then figure out their temperatures. And the hottest stars that we see are about 50,000 Kelvin. For comparison, the sun is about 5,800 Kelvin. So this is 10 times as hot as the sun. The coolest stars are about 3,000 Kelvin. And the reason we can't go any cooler than that, we're going to learn next time that it takes a certain amount of mass to cause that star to start fusing to become a star. So this is important. Here's the definition of a star. Ready? A star is anything that generates energy through nuclear fusion. So a star is anything that generates energy through nuclear fusion. So a bomb, a hydrogen bomb, but takes those hydrogens and smashes them together and releases all this incredible amount of energy. We'll go into detail about that next time. But that bomb is a star. When I detonate that bomb for just a split second, I have a star on the surface of the Earth, and that's kind of a sad face day for a lot of people. But anything that generates its power through nuclear fusion is a star. If the star is low enough, if the object doesn't have enough mass to fuse, then it's not going to become a star. And so by the time I get enough mass to have a star, the coolest you can possibly get is around 3,000 Kelvin. So we won't really find any stars that are going to be cooler than that. You also know how to calculate the size using the Stefan-Boltzmann law. Remember, if I know the luminosity and I know the temperature, then I can use the formula to get the size. So once I do that, we find that the smallest stars are about 1/10 the size of the sun. These are pretty tiny. This is like Proxima Centauri that's next door to us, things like that. The largest stars then are going to be about 1,700, and there's not very many of these. Ones greater than 1,000 solar radii are actually pretty rare. But that's the largest stars that we found so far. So we classify these stars then based on their size. And so a dwarf star is anything smaller than 10 times the radius of the sun. Our sun is a dwarf. Our sun is a dwarf star. A giant is anything that goes from 10 solar radii to 100 solar radii. And then a supergiant is anything that's from 100 to 1,000, and then that 1,700 one that we talked about, it's technically called a hypergiant, but there aren't really enough. There's maybe, 2, 3 that we found in the entire 100 billion stars out there. And then normally we're going to include the color that it gets due to its temperature. So we'll talk about a red giant or a blue supergiant, a red dwarf or a blue dwarf or a white dwarf, things like that. So that color then is giving us an idea of the temperature. So those can be kind of hard to say. So we talk about luminosity class, and it's a little deceptive because when we're talking about luminosity class, we're really talking about the size of the star. And so the reason why you can understand that, let's suppose that I have two stars that are the same temperature, and this star is much more luminous. Well, the only way that's possible, you know, is if it's really big. So the luminosity class is also a measure of the size of the star. So type 1, Roman numeral 1, are supergiants. There's only 3 that I'm going to expect you to know out of the 5. Type 3 are our giants. And then type 5 are the dwarfs and also main sequence stars. That's a concept I'm going to introduce today. So in between these two then, type 2s are called bright giants and type 4s are called subgiants. We won't be working with either of these two. What I want you to remember is a type 1 is a supergiant, a type 3 is a giant, and a type 5 is either a main sequence or a dwarf. So just to give you some idea of the sizes here, so this is Earth. Right here, that's the dot the size of Earth, and that's the sun. So you see that the sun is, oh my God, huge compared to the Earth. But a giant star like Aldebaran here is much bigger than the sun. And a supergiant like Betelgeuse that we've been talking about is much, much larger than the sun. And so here they're showing you this is the orbit of Mars. So remember I told you that Earth, Venus, Mercury, and Mars would all be inside the star. So that's how huge these things are. So when we put the luminosity and the temperature on a graph, like we were talking about, you know how we could take the curve and plot the brightness versus the temperature, but really all we cared about was that point, that one point right up at the top peak. So that's what these are. So if you think about, you know, this dot right here, for example, that's a peak that comes up to here and then comes down. But this would be really confusing if I tried to draw the peaks, and I just don't need them, so let's be lazy. So all I'm going to do is put a dot then for the top of the peak. Now I can plot hundreds of these here. So if I plot the luminosity on this side and the temperature on the x-axis here, we find that 90% of all the stars out here lie on this little strip, this strip of stars here that we call the main sequence. So 90%, that means that of all the stars out there, they spend 90% of their lifetime on this main sequence. So the definition of a main sequence star is a star that is stably fusing hydrogen into helium. Basically, this is when the star it's been born, it's stable, it's turning on, but it's not yet started to die. As soon as the star starts to use up its hydrogen fuel, then it's no longer going to be stably fusing that hydrogen into helium, and it's going to start to die. What we're going to learn in a couple of weeks is that as it starts to die, like this might be our sun, it will become a giant. And then it'll go down here, maybe something we call the horizontal branch, but then it'll eventually become a supergiant. And then after our sun is dead, when the core of the star is all that's left, and it's just this, you know, big piece of charcoal out there, then it's going to be a white dwarf. So these 3 areas then, supergiants, giants, and white dwarfs, are dead stars, or stars that are dying, as the case may be. But as a star lives out most of its life then, it's going to live it on the main sequence here. Now we need to talk about the scales here on the luminosity side, because now we're actually going to have to start reading things off. Remember how I told you how there was this big difference between 10 to the minus 4 and 10 to the 6 for the luminosity? It's just a big range. If I wanted to try to plot that on a graph, it would be really, really stretched and really, really big. So instead what we do is we plot it using a logarithmic graph. And don't let that scare you. Basically, it just means this is 1. The next mark on here in between would be 10. This is 100. 10 to the second is 100. In between is 10 to the third, which is 1,000. This is 10 to the fourth, which is 10,000. 10 to the fifth, which is 100,000. And 10 to the sixth, which is 1,000,000. Going in the other direction, 10 to the minus 1 is 0.1. 10 to the minus 2 is 0.01. 10 to the minus 3 is 0.001, and 10 to the minus 4, which remember is going to be our coolest, is 0.0001 from that. And if you look in the resources page, I've got an HR diagram there for you now. So when you print that out, what you might want to consider doing is making sure that you write in the numbers here. If I can, I'll try to modify to put that in for you. But write in those numbers so that you can see 1, 10, 100, whatever. So if I've got something that has a luminosity of 563, I'm just totally making that number up. This is 100, this is 1,000 right here. So it's going to be, somewhere in between. It's going to be somewhere like right about in here. Okay. The temperatures then are on scales that we're used to thinking about. 2,000 down here, of course, 3,000 is going to be about as cold as we can get. So that one is probably actually a brown dwarf. We'll talk about that later. But then we've got 4,000, 6,000, 8,000, 10,000. And then for the sun, then we should be, right around 1 solar lumen and around a little less than 6,000 Kelvin. All right, let me move this out of the way here. So when we start looking at stars, when we start studying these a long time ago, we would look at the spectrum of the star. And you guys remember, here I have a rainbow with black lines on it. What kind of spectrum is that? Is that a continuous spectrum, an emission spectrum, or an absorption spectrum? That one's going to be an absorption spectrum, and so are most stars. And we're going to learn this next time. Remember that the star has a core that's generating its energy. It's really hot and dense. And as that energy comes through the cooler, lower density atmosphere, that lower density atmosphere absorbs particular lines here. Well, they started classifying these by spectral type, and they said, okay, we'll call these Class A, Class B, Class C, Class D, Class E, and so on and so on. As we started looking at the spectrum a little more carefully and learning more about it, we realized that, for example, and maybe the A's and the C's were the same. And so we combined those together. By the time we finished combining all of the ones that were actually, turns out, the same kind of star, we only had 7 left. Then we said, okay, well, we've got these 7, but we realized that the temperature of the star goes in a nice even progression if we put them in the correct order. So some people call this the astronomer's alphabet. So the hottest one, it turns out, was a type O. The next hottest was a type B. Then A, F, G, K, and M. We'll talk about that more in just a little bit. But the key thing is that we classify them actually by looking at the lines that we see. So here, for this type O star, it's very hot. So we're getting these what are called ionization lines. But I don't get molecules. It's too hot for molecules to form. Class M stars, on the other hand, they're much cooler. And they're cool enough, 3,000 Kelvin or so, they're cool enough that we can actually get molecules to form. Well, molecules mean you have more places that you can vibrate, electrons can go, you're going to get more lines. So when I see a spectrum that looks like this, I can say, aha, that's a type M. Now, of course, I can also get the temperature by looking at the peak color of the rainbow that's behind it. And then if I can also get the luminosity, I can actually plot that on an HR diagram. So that HR diagram allows me to not have to do look at the spectrum of all these millions of different types of stars. So let's look at the spectral classes. I'll move the video back up here. Let's look at them. So O, B, A, F, G, K, M. You must memorize this. I don't ask you to memorize much in the class, but you do need to memorize this. And so what most people do is they'll come up with a mnemonic to help them remember. The classic one, which I don't particularly like very much, but it's "Oh, be a fine girl/guy," depending upon your persuasion, kiss me. Meh. We had a competition to let students actually come up with their own, and the best one I heard was, "Oh boy, another final's gonna kill me." So whatever you need to do to remember from the hottest to the coolest, O, B, A, F, G, K, M. Some of Sally's students, my wife, came up with one. Our best astronomer finally got Kilo married. Don't like that because that makes her the best astronomer. But whatever you need to remember it. So make something up and then that'll help you remember this. The O's are the hottest, the M's are the dimmest. You are the coolest. You must memorize this. Make sure that you've got it in order. This is very important. I am going to assume from here on out that when I say an A-type star, you know where that falls in this. Okay, now we also break that down into subtypes. So an O9 is just a little bit hotter than a B0. So it's just actually a scale as we go through here from O0 being the hottest to M9, which actually should be over here, is going to be the coolest. Okay. So when we look at these, then the O-type stars are the hottest, the M-type stars are the coolest. So that means these are going to be our red stars. Let me get my picture to come back. There we go. So our hot stars here, they're going to be blue, and these are going to be our red stars. Remember, there's only two colors in astronomy, hot and cold, red and blue. The O-type stars are the most luminous stars. They're the brightest stars. Now remember, we're talking about luminosity. We're not talking about how bright it seems to your eye. We're talking about how bright it really is, how much energy it's putting out. If it's a long way away, it still might look dim. The flux that we get might be small, but the star itself is still really bright. It's still really luminous. So don't get confused. No distance coming into play here. The M-type stars are very, very dim. The O-type stars are very high mass. And if you think about it, that makes sense. These things are hot because they're squeezing harder. And we'll talk about this more next time. But the harder they squeeze, the more energy they're producing. Well, the more mass you have, the harder you can squeeze. So these things have a high mass, whereas the M-type stars have a low mass. This also relates to their lifetime. Now, you would think that the O-type stars would last longer because they've got more fuel. They're bigger, right? Turns out these are actually the shortest lived stars. And the reason for that is they're so hot and so luminous, even though they have more fuel, they're burning through it a whole lot faster. So these things, these O-type stars, might live for 10 million years. That's it. That's probably not even enough time for life to develop on any planets around them. Whereas these M-type stars, they can live for 10 billion years or even 10 trillion years from that. So anywhere from millions to trillions of years. And you'll be working with that in the simulator for that. But so you can think of O-types as being the Marilyn Monroe of the sky. They burn hot, they burn fast, they burn out. M-type stars are just chilling, man. So this is the universe giving you a message. You know, if you just lay back, you're chilling, you stay cool, stay calm, you're going to live a whole lot longer, man. The universe is telling you this, not me. All right, our sun is a G2 star. So we're pretty much an average star. There are not actually very many of these O and B type stars simply because they don't live very long. The most common star is actually going to be an M-type star because they live like forever, longer than the universe has been around. So we're kind of right here in the middle of it. So just to give you an idea of the difference that the size makes, these luminosity classes make. Here we've got three stars that are basically the same temperature. So they're all going to be the same color. They're all going to be kind of a reddish orange from here. So even though they're 4900, 4500, 4300, they're all going to be about the same. So they're all going to be this reddish orange. However, this star, Epsilon Eridani, which by the way, if you watch Star Trek, that's Vulcan, but it's got a very low luminosity, 0.3 solar lums. So this thing's actually dimmer than the sun. Well, that's because of its size. It's actually smaller than the sun. This particular one right here is a red giant. And so it's got a luminosity of 110 times the size of the sun, yet it's the same temperature as Epsilon Eridani. So that the only way that's possible is if it's really big. And you see, if you do the math here, you can see that it's 21 times the size of our sun. And then Epsilon Pegasi, again, same temperature, same type, but it's much, much brighter, 4,000 luminosities. Well, then this thing must be truly huge. And in fact, it's a supergiant. Don't worry so much about the A and B. We won't worry too much about that. The type 1 is what we're interested in here. Good. All right, move the video down here again. So all of these are main sequence stars. All the ones that lie on that curve right there are main sequence stars. But you can see that even among the main sequence stars, there's a big difference in size. And that makes sense, right? Because those lines are showing me the sizes from there. So Spica, which is one of the brighter stars in the sky, is a B-type star. It's a main sequence star, it's stable, but it's very hot. And so if we think about the curve drawing over here, those blue stars up at the top of the main sequence, those are going to be the hottest stars. Whereas the M-type stars down at the bottom of the main sequence, those are going to be the coolest stars. And if you've got your HR diagram out, then you can see that. So let me show you that right quick here. So the blue stars here, even though it's a main sequence star, Spica is way up here, which means it's really bright and it's really hot from there. On the other hand, those M-type stars are going to be way down here, so they're going to be really dim, they're low on this scale, and they're going to be really cool from here. Okay. Sirius, which is the brightest star in the sky, is an A-type star. Now, it's not as luminous as Spica. So why is it that Sirius is actually brighter than Spica? Well, it's closer. Do you see that? So how bright it seems to your eye depends upon the distance. But in reality, Spica is actually brighter than Sirius. If we brought Spica up to be the same distance away as Sirius, it would be outshining Sirius by a whole lot. Our sun then is a G2. It is also a main sequence star. That's what that V means. And then Proxima Centauri, which is the nearest star to our sun. Now remember, the Alpha Centauri system is a trinary system. It's 3 stars. So there's 2 Alpha Centauri, A and B go this way, and then Proxima Centauri orbits the pair. And right now, Proxima is on the side of its pair where it's closest to us. So Proxima right now is our closest star. Eventually it won't be. One of A and B will be our closest. But right now Proxima is. And you see that it's an M-type star. And even though it's a main sequence star, it's going to be around for, trillions of years. It is teeny tiny compared to the sun. So if we find any planets that might be habitable around here, they're going to have to be very close to the star, just because they're not putting out a whole lot of energy there. So the mass determines both its size and its lifetime. You see that Spica has a mass of 11 times the mass of the sun, whereas Proxima Centauri is like a little over 1/10 the size of the sun. So this thing is squeezing so hard, it's generating a whole lot of energy, so it's burning through its fuel really fast. And so that means this is not going to live very long, 10 to the 7th years. That's about 10 million years. Whereas our sun is going to live 10 to the 10th years. That's about 10 billion years. On the other hand, Proxima Centauri is going to live about 10 to the 12th years. That's 1 trillion years. So considering the universe isn't even 1 trillion years old, some of the very first stars, the very first M-type stars that were ever created are still around. On the other hand, when the dinosaurs 65 million years ago turned their telescopes to the sky, they didn't see Spica. It hadn't been born yet. So the difference in the lifetimes of these depends strictly upon the mass and how fast it's burning. All right, so this is the HR diagram. This is going to be similar to what you're going to be working with. And again, I need to lower my camera view here. So luminosity increases this way, temperature increases this way. Now that makes some people nervous. They don't like that something's increasing this way. Remember, what's actually increasing to the right is the wavelength. Short wavelengths are blue, and so they have a higher temperature. Long wavelengths, which are over here, as you might expect, are red, so they are cooler, right? Okay, so which of these stars is most like our sun? Pause the video, so I'm looking for A, B, C, or D. Pause the video, think about it, and then see what your answer is. Okay, so we've got star A up here, star B here, star C here, and star D here. Well, our sun is a yellow main sequence star. It's a green main sequence star. It's got 1 solar lumen because it's the sun. It's a G-type, so B must be the star most like our sun. See how we can see that. But here we can actually read off the temperature and read off the luminosity. Or if we have the luminosity and temperature, we can figure out what its spectral type is. All right, which star will have changed the least 10 billion years from now? Pause the video, think about it. All right, star A, star B, star C, or star D. Which will have changed the least? So that means which one has the longest lifetime, right? The longer the lifetime, the less it's going to change. In 10 billion years, our sun will be dead. So certainly that one's not good. This one would have long since been dead. So it must be star C. These cooler, lower luminosity stars are going to live a whole lot longer. So 10 billion years, that's nothing out of 1 trillion years. So this star isn't going to have changed at all, star C. Which star can be no more than 10 million years old? Pause the video, think about it, work it out. Well, remember, the lifetime of these O-type stars here is very short, less than 10 million years. So since they only live for 10 million years, this one cannot be more than 10 million years old. Now, it is possible that star B or star C is a new star, and it might be less than 10 million years. It's just going to live for a whole lot longer after that. But star A cannot be more than 10 million years. And we're going to use that later on in the course. Okay, so do you see why? All right, so if we plot the brightest stars in the sky on an HR diagram, so here's our luminosity, here's our surface temperature. And here we've gone and we've put in the standard notation numbers to help you out a little bit. If we plot the brightest stars in the sky, there are very few M to G type stars. And you see that almost none of them on the main sequencer here. Most of the bright stars that we see are these A and B type stars. We don't see many of the O type stars just because there aren't any. They don't live very long. These giants we can see, even though they're cool, they're very bright. So the giants then are going to be bright, and so are the supergiants that are way up here. Okay, so we don't see these bright stars, or the G and M type stars. So if you were going based on strictly what you see with your naked eye, so the brightest stars are what you see with your naked eye when you go outside. You're looking at these. You might say, oh yeah, okay, most of the stars out there are B's and A's or giants and things like that. Our sun is kind of weird. It's like one of the coolest stars that we could possibly see. But when we plot the closest stars, we find the opposite case. Very few of those bright stars that were up here are near us, Sirius, Altair, or Procyon. Those aren't going to be near us. Here's Alpha Centauri. So those are fairly close, but all these giants, all of these B's and A type stars, most of them are not anywhere near us. The only reason they're bright in our sky is because they are luminous. They are intrinsically bright. They're putting out a whole lot of energy. So they can be a long, long, long way away, and you'll still see them. So we're seeing all of the bright stars that are in our neighborhood. It's just because they're so bright. But most of the stars are actually M-type stars. And most of the stars that are actually nearby to you, you can't even see with your naked eye. How weird is that? The closest stars to us, the ones that are actually in our solar neighborhood here, are so dim you can't see them at all. So Proxima Centauri, for example, is way down here. Barnard star, which is one of our closer red dwarf stars, is over here. So this is most of the stars in the universe then, we think. Most of the stars in the universe then are going to be these G to M type stars. See if that makes sense. Let's say that I have a cluster of stars, and we'll get into how these are formed later, but let's say I've got this cloud that creates a whole bunch of stars, and let's say that it creates just as many O-type stars as it does M-type stars. It doesn't, but let's pretend that it does. So these stars get made. Well, as we move through time, those O stars die out. The M-type stars are still there. Those O-type stars, when they explode, they put out gas back into the universe that then can form more stars. So now I'm going to form more O through M-type stars, but I've still got this generation here. These stars die. Now I've got even more M-type stars. This creates a few more. I get O to M. And you see that over time, I'm going to have fewer and fewer and fewer O-type stars, but I'm going to have more and more and more M-type stars just because I've got more generations, because those M-type stars can live for so much longer. So our universe is, you call it 14 billion years old. So out of that amount of time, none of the M-type stars that have been created since the beginning of the universe have died yet. Whereas the O-type stars, they live almost no time at all from that. Okay, let's move the video back up here. Okay, so here's some tools that we've been using. These apply only to main sequence stars, so you cannot use this with a red giant or with a supergiant. So these only apply to main sequence stars, and this is the Stefan-Boltzmann law that we're familiar with. To get the size of the star, you need to find the luminosity, which remember, you'll have to get from the flux and from the parallax. Sometimes we'll just give you the luminosity. And then the temperature then, you get from Wien's law, find that peak wavelength. You can also now read these off from the HR diagram. The mass of the star then depends upon the luminosity of the star. So this is new. This is a new tool. So you take the luminosity and you raise it to the parenthesis 1 divided by 3.5 close parenthesis power. Okay? So be careful. Don't forget these parentheses. If you do L to the 1 and then divide the whole thing by 3.5, that's not going to work. It's got to be L raised to the 1 over 3.5. And then to find the lifetime, it also depends upon the mass. Remember that the mass is basically controlling how much energy it produces. That's why if we know the luminosity, we know the mass. And then it also is determining how fast it's burning through that. So you take the mass of your star, which you just calculated here, raise it to the negative 2.5. Okay, so raise to a power and then negative sign 2.5. And then multiply by 10 billion. So this part here is, you can think of that as solar lifetimes. So if you get a 1, that's the same length of time as the sun. But we want it in years usually. So just multiply by 1e10 That's multiplying by 10 billion, and that'll tell you how many years the star is going to survive. All right, so that's it for this one. Download the star classes worksheet, the practice sheet from Canvas that looks like this. And on this one, you're going to be classifying the star using the HR diagram that you'll find in the reference section. And so that there's a nice color HR diagram, or you can look at the video or the PowerPoint. And then we're going to have you, if it's a main sequence star, we're going to have you calculate the radius, the mass, and the lifetime using those tools that we just talked about. And then this is testing your understanding of the OB-AFG-KM, the spectral types from that. Okay, so work on that. Let me know if you have any questions, and we'll see how that goes. Okay, so now that you understand what star classes are, from here on out, I'm going to be talking about O stars, I'm going to be talking about K stars, I'm going to be talking about M stars, and I want you to have a good idea in your mind what that is. So if I say an O star, you should be thinking of something really big, really hot, and really blue. Okay. Remember that we're only generally talking about the spectral types when we're talking about something that's on the main sequence, and that's going to be important later on. So if I'm talking about a G2V, like the sun, then that's going to be a main sequence star. It's going to be a main sequence 1 solar mass star. Okay. So try to keep things in mind. Also remember, I want to caution you, those tools that we just talked about with the radius, the mass, and the lifetime, those only apply to main sequence stars. So if it's not a main sequence star, you can't use those. So you can't use that for a red giant or for a supergiant. It's because the processes that are going on inside are different. The star is no longer stably fusing hydrogen into helium. Okay, that's it for this one. We'll see you next time.